What if this is a structural steel, an A36 structural steel, which means it has a yielding strength of about 36 KSI. And what is the ultimate strength approximately of a structural steel? Does anyone remember? Okay, 66 KSI. We can look that up if you want, but in our reference material here, up here at the top, okay, we have 36 KSI for structural steel and 66 for your ultimate strength. What that means is you have a lot of deformation that this material can do before it reaches the amount of stress that it takes to actually break it. This is what's called a ductile material. Structural steel is a very ductile material. It means you can bend it and stretch it quite a bit before it actually will start to, want to crack. Okay? So if you have that in mind and you go back to our problem that we're trying to solve here, and actually let me go to the SolidWorks thing. Where's the only material that's reaching these high stresses? Yeah, like not very much of this material is reaching those super high stresses. And what if you go out here? Like it's hard to see it here, but it says out here, you're at more like 4 KSI out here. Right, or maybe, like 2 KSI or so out here. Okay? So what do you think I'm getting at with this? So where I'm going with this is this. It's not always the end of the world if your material yields a little bit locally at one little spot. Right? We're not saying it broke. We're saying it deformed permanently once it reaches those high levels of stress. So think about what would happen on this if you reached high levels of stress enough to deform it permanently right here in this little zone. So then it deforms permanently. What happens then? Okay, so what it'll do, it'll move stress away from that zone and force the other material that's still here in this cross section, right? It'll force that material to carry more stress as it yields a little bit, and that transfers the stress outward into the material that's not currently holding a lot of stress, right? And so here's the principle we can draw from this. There's a lot of times where when people design with ductile materials, they ignore stress concentrations. And this is exactly why, right? If you're designing with ductile materials, you sometimes, as a matter of fact, very often you don't care what this maximum stress is as long as it's super localized, because your presumption is once I put it in service, it's going to yield a little tiny bit right there, and that will equalize the stresses across all the material that's there available to hold the load, and I don't really care if it yields a little bit locally right there in one spot. Okay? I know that's a little bit hard to think about, but there's, one of the reasons I tell you this is I'm trying to actually give you a little more confidence again in our earlier calculations we did in the quarter. Because we did things like, how much force can it hold before it breaks, right? And, now that you're applying this kind of thinking to it, thinking, I wonder if we considered stress concentrations on all those problems that we did earlier in the quarter. What I'm going to tell you is, if they're made out of ductile materials, there's a pretty good chance that it wouldn't matter anyway. Because the presumption would be that the material would yield a little bit, and then that would just transfer load that had been concentrated all at one little spot into more of the material, and you're fine. Okay? And that was about all I wanted to say. Any other questions? Yes, sir.
What about the other forms of, like the shape up there where you have the bolt-looking one and the one with the 2 divots?
Okay, so you might be saying, what about these other ones that are here in the reference material? So let's kind of scroll through here. So these are the ones we looked at just now. Okay. Are there any other ones? Here's another one. What's this one? Whoop. Okay. It's the same geometry as what we just calculated, but instead of carrying an axial force, what's this one carrying? A bending moment, a flexural influence that's happening on it. Okay? And it has its own set of curves for dealing with that flexural version. Okay, there's another one down here somewhere, right here. This one is for torsion. So if you have a shaft that reduces in diameter and you're twisting it, right? How do you know that this one is torsion versus the other one that's a bending moment?
Because it shows you the forces applied.
Okay, this one's pretty obvious. It's showing you that you got these two bending moments that are being applied to it. This one's a little bit less obvious because they didn't do a real good job on this one of labeling the torque. So for this one, let me just go ahead and make that clear. Say this one's for torque. And if you want a little clue, other than, you know, me telling you that, they did show you that it's a roundish shape by kind of how they drew it, right? It does give you the idea that this shape is circular. But anyway, I know that may not be, you know, enough or totally desirable, but let me just go ahead and say this entry that we've got here is for torsion. And this will allow you to calculate what these stress concentration factors are for that. Okay, here's another one. What's this one? Whoop, come on. What's that one there? Okay, it's another flexural one, but what's the difference on this one? It's basically got two little notches cut in it, right? So it's a little bit different than the last one, the last flexural one that we looked at. This is also, let me say this, these charts that we have in your reference material that you'll be able to use on an exam or whatever, these are by no means exhaustive, right? There's actually books and books that people have put together of charts like this for various kinds of cases. We just picked a few of them that might look interesting, make it easier for us to write a particular problem. And we threw those in the reference material. But once you know how to read one of the charts, the process is the same regardless of what kind of geometry you're looking at. Okay. We good? All right, let's call it a day.